Okay, trying to wrap up chapter 1 here. Get that on there and stable. Okay, so the last thing we want to talk about here in chapter 1 is a physical property or quantity related to a particular material called density. And density fits kind of nicely in with what we've been talking about in terms of problem solving conversion factors, because density really is a conversion factor in and of itself, and it helps us relate the quantities of mass and volume for a particular material. So the definition of density is it's the ratio of the mass of material to a particular volume of that material. So in terms of a fraction, density is mass divided by volume, right? And in terms of units, that's often grams divided by milliliters, the way we measure mass generally being in grams, and the most convenient way to measure volume is milliliters. Now, you will sometimes also see grams per cubic centimeter, particularly for a solid. If you know its dimensions, it might be easier to calculate volume in terms of cubic centimeters. But keep in mind, milliliters, cubic centimeters mean the same thing. That's the same amount of volume. And if you're measuring the density of something that's particularly diffuse, like a gas, that often will be in grams per liter. So you're just taking a larger volume of the gas so that you have a mass that makes a little more sense in terms of how much is present in that particular volume mass-wise. Okay, now one thing that's different about density is we might have to use the units just to figure out where to put pieces to solve a problem. Right? So we're not really canceling out units like we've seen, we're just kind of injecting them in the right place, which is the case in these first two examples. So if we have a copper sample and we record its mass, 44.65 grams, and then we also measure its volume, in this case the volume is 5.0 milliliters, if we're asked to calculate the density, right, we can't do it by canceling out units, but we can do it by putting units in the correct position. So we know density is defined by grams per milliliter. So if we take the mass, put it on top of a fraction, 44.65 grams, take the measured volume, put that on the bottom of that fraction. Now we've got the correct units. Nothing canceled out because we can't cancel grams with milliliters, but we do stack those units together to give us the quantity we're looking for. And since that's the case, we just need to do a division here. So 44.65 divided by 5. Now the volume here, 5.0, is two significant figures. So my calculator here says 8.93, but remember we want to round that to 2 sig figs, so I'm just going to put 8.9 grams per milliliter as my answer for the density of copper. Right? And really important to have the appropriate units there always on your answer, but particularly when you're describing density, because again, this is a ratio. It's that much mass would correspond to 1 milliliter of the copper material. Okay, now the second problem here is similar, but it doesn't quite give us the same set of information. It gives us a way to determine the volume of our sample so we can get to density. So we've got a lead weight that's used, that could be used by a scuba diver, give you some weight in your belt as you're descending. It's 226 grams. Now we don't directly have the volume, but we have some information about how much water the weight displaces when we drop it into a graduated cylinder. So there's a graduated cylinder that has 200 milliliters of water in it. When we put the weight in that graduated cylinder, the water level goes up to 220 milliliters. So anything that sinks completely in the water is going to cause the water level to rise the same amount as its volume. So to get the volume of the lead here, what we need to do is subtract 220.0 milliliters. That is the lead and the water. If we subtract the 200.0 milliliters, that is just the volume of the water. So subtracting there will give us the volume of the piece of lead. Now, once we have the volume of the piece of lead, we have the same data we had in the first problem. The mass is 226 grams. The volume is 20 milliliters. Density is grams over milliliters, or mass per unit volume. So if I take 226 grams, divide by 20.0 milliliters, that will give me the density of the lead sample. So 226 divided by 20 is 11.3 grams per milliliter. Right now, both of the pieces of data we have here end up being 3 significant figures, so 11.3 is just fine, because that is also 3 significant figures, right? Important thing to recognize here, even though both of these were 4 sig figs, since this is a subtraction, it's limited by place. So our answer is still limited to the ones place. Our answer is a 3 significant figure number, even though both of the ones we started with were 4 significant figure numbers. Okay. So calculating density is one thing that we might need to do, but because of the way the units are ratioed in density, density also is a conversion factor that we can use for other calculations. So I have 2 more examples here of how density might be used in a problem. So the first one asks us, how much does 6.85 milliliters of mercury weigh? So if I start with 6.85 milliliters of mercury, so Hg here is the chemical symbol for mercury. And then we're provided the density. Density of mercury is 13.6 grams per milliliter, right? I want milliliters on the bottom here to cancel out the milliliters I started with, and that means I can put the mass of my mercury sample on top, right? And again, there's this kind of understood or hidden 1 in the bottom of that ratio, and you don't have to write the 1, you just have to know the units go there, because that's what's going to cancel out, right? Milliliters cancels out. This would give us the mass of this mercury sample. So 6.85 times 13.6. So calculator says 93.16, but 3 significant figures in the data. 3 significant figures here in the mass part of the density as well. Now, the per milliliter, that's considered exact or defined as 1 milliliter, but this answer should just be 3 sig figs. So 93.2 would be what we'd get when we round to that 3rd significant figure. Okay, that version fairly straightforward because we use the density the way it's provided in the problem. Second example, this is the one that's a little trickier because we need to invert the information given in the density, but let's show that as we go through the problem. Okay, so we want to calculate volume, and the volume of, in particular, this chunk of silver with a certain mass. So given the mass, that is a good place to start our problem, 4.53 kilograms. Now we are provided the density in grams per milliliter, so if we get our mass to grams, we'll be able to use the density in our calculation. So let's cancel out kilograms and change our units to grams. 1 kilogram is equal to 1,000 grams. So that would cancel out kilograms. Now what we have for our unit here that we're using to kind of guide our calculation is grams on the top. And that means we need to put grams on the bottom here in order for it to cancel out. Now if we use the density, we can relate grams to milliliters. But what that means is the 10.49 grams is the bottom of our fraction. The per milliliter, or the 1 milliliter, is on top. Now again, that's an equality. The density is telling us 10.49 grams is equal to 1 milliliter of volume. So we can flip that the other way as well when it's appropriate for the units we're trying to cancel out. And in this case, it allows us to cancel out grams and leaves us with volume units, which is exactly what we want. So punching this in, 4.53 times 1,000, and then divided by 10.49. 3 significant figures at the start, exact number here, 4 significant figures here in the measured part relative to the exact one, so 3 sig figs is my limit. So based on my calculator answer, 431.839 and on, I want to round that to 3 sig figs, so 4, 3, and then I'll round that one up to 2, and that would be 432 milliliters for the volume of that particular sample. Okay, that wraps up chapter 1. So next video will be chapter 2.